Did you know that bottlenose dolphins can sleep while being awake? They do so by having half of their brain sleep at a time. Now in this video, we're going to be continuing to talk about the nervous system. So remember in last video, we had Stipe Miocic, an MMA fighter, get punched by this random guy in the street, right? And we saw that when he gets punched, when he gets punched on his shoulder, for example, what happens is he can feel it. He can feel it because there's a neuron or a nerve cell that senses this punch that was on his arm, and it sends it through a signal to his central nervous system. So then here in the central nervous system in his spinal cord, another nerve cell will pick up or take that signal and transfer it continuously to the brain, okay? And then when this signal reaches his brain, he will feel pain, okay? His brain will understand it as pain. Then his brain will make a decision of how to respond and send that signal down. But this time it will send it down to a motor neuron, okay? A motor neuron is a neuron that goes to a muscle to allow a muscle to react, okay? So this neuron here was a sensory neuron that basically picked up what happened and transferred it to the brain, and transferred it to a neuron in the spinal cord called a relay neuron that sent it to the brain. Now this relay neuron will send a signal back down and transfer it to a motor neuron that will cause this guy's muscles to contract so he can punch the guy back, okay? So I've been talking now a lot about this signal. What do I mean by the signal? What exactly is being transferred through the neuron, and what exactly is being taken up by the next neuron to transfer to the brain, and so on. So we're going to be talking about what the signal exactly is. But in a nutshell, what this signal is a positive charge. So for example, let's say he was punched, the signal was transferred to his brain, he understands that he was hurt, and now he wants to punch the guy back. So his brain will need to send a positive signal into this neuron. This neuron will transfer this positive signal all the way down, and then the next neuron, the motor neuron, will take this signal and transfer it to his muscle to allow it to contract so he can punch. Okay, that's all we got to care about, this positive charge, this positive signal. When your muscles do not have a positive signal, they're relaxed. That's why when you're sleeping, you have no brain activity, you have no muscle, you have no positive signal being sent to your muscle. But when you decide to send this positive signal, that allows your muscles to contract. Your muscles need this positive signal. So we're going to talk exactly about how this positive signal is formed and how it's transferred in your neuron. Okay, so here we have these two neurons, 1 and 2. Okay, you can see they're attached to each other. This neuron here kind of represents the one coming from his brain. Okay, the next neuron, this one, represents the one going to his muscle. In this video, we're going to talk about how this positive signal is moved throughout one neuron. Okay, so inside neuron. In the next video, we're going to talk about how this signal is transferred from this neuron, from one neuron, to another one. Like what exactly happens right there, okay? If we know both of these things, we know exactly how a signal is transferred from your brain through the neurons and across neurons to your muscle to allow it to contract, okay? So that's it. It's quite simple. So here I have a diagram. We zoomed in onto this one section to see how this positive charge is formed and how it moves, okay? Because once you know this, you know how it happens all throughout, okay? It's the same thing all throughout a neuron. So to start off simple, because it's related to charges, I know a lot of people taking biology, including me when I took biology, I didn't really understand what charges meant because that's a physics thing. So I'm going to make what charges mean a little bit simple here. So let's say this is the inside of your neuron, or the inside of your axon, because remember this long pipe is an axon, and then this is the outside of the axon, okay? Now, basically, if there's nothing inside your axon and nothing outside the axon, what will the charge be? So this thing here, this machine here, measures the charge on the inside of your axon compared to the outside. So it measures the inside compared to the outside. So if the inside and the outside have no positive or no negative charge, then what will this charge be? 0. Okay, because the inside is neutral compared to the outside. Now, what if we take a molecule, okay? This molecule is called sodium, okay? This element is called sodium. This ion is called sodium, okay? So what if we put some sodium, so it's Na plus, by the way, Na plus, so it's positively charged because it's got a plus charge. What if we put some sodium ions inside our axon? What will the inside be now compared to the outside? The inside will be positively charged compared to the outside, right? Because we have these sodium ions, these positive charges on the inside, but nothing on the outside. So we can make it positive. And let's give it a random value, plus 50, okay? This value is just random. I'm just giving it randomly. But it's got to be positive. Now let's say we have these sodium ions instead on the outside. What's the charge going to be on this machine now? Now the inside is negative compared to the outside because the outside has a lot of positive charges. So the inside compared to the outside is negative because it's got no, even though it's got no negative charges on the inside, it's neutral. Compared to the outside, it's negative. Okay, so remember, this machine measures it compared to the outside. So if the outside's positive, then the inside is negative compared to the outside. So we can make it now negative 50. Okay, the inside is negatively charged compared to the outside. Now let's put two of them on the inside. Now what's the charge of the inside compared to the outside? Technically it's neutral because they both have the equal number of positive charges. So the inside compared to the outside will be equal. So it's 0. So far so good, right? Now let's add one more thing. Let's add another ion. This one now is called potassium. So it's K+. Okay, the symbol for potassium is K+. So it's also positively charged, just like sodium. Now, let's say we add this K+ on the outside of the axon. What will the charge of this thing be now? Technically now the outside has 4 positive charges, whereas the inside has 2. So the inside is negative compared to the outside. So it's going to be negative charge. Let's just give it a value. Sorry. Give it a value of like negative 30. But let's move it now, this other positive charge on the inside. Now, the inside is positive compared to the outside, so we give it positive 30. Okay, do you get this concept? If you understand this concept, everything will make sense for the rest of the video. Now, let's look at this membrane. You see this membrane, so it's basically the membrane of this axon. It's got these channels. So this yellow one here is like a channel, meaning sodium, so this one can pass through this channel when it's open. So if this channel is closed, sodium cannot pass through it. This one here, this green one, can allow potassium to pass through. Okay? But only when it's open. Now this one here is something quite interesting. So we're going to talk about this one just now. Now, remember I said that for your muscle to be activated, it needs to receive this positive charge, right? So it needs to have this positive charge transfer all through the system until it reaches this muscle. Once this muscle receives this positive charge, it will contract. Now, the thing is, when we're doing nothing, our neurons are actually negatively charged. So that's why our muscles can't contract, because it's always negative. Okay, so it's normally negative. Specifically, it's actually negative 70. Okay, negative 70 millivolts. Okay, MV, millivolts. Now, why is it like that? Because I'll tell you, in our axon, we only have these two ions, potassium and sodium, that we need to worry about. Okay, these two, sodium, potassium. Now, why is it negative 70? Why? Because if we open all these channels, wouldn't everything just even out? Like, wouldn't we just have this potassium flow out so that it's even on both sides by diffusion? Because right now, for example, there's a lot of potassium, and we know that when we open the channels, they will flow out and everything will become even. Because even now, if we open this one, these sodium ions will not want to flow in because there's already 2 on the inside. They want to be equal. So wouldn't it be 0? So technically, yeah, by logic, you would think it should be 0 because everything should just even out when all the channels are open. But that's not how it works. Let me show you how it works. This would only be true if only these channels existed. But unfortunately, this channel exists. And this channel is what's going to make this charge -70. Let me show you how. So when you're doing nothing, when you're sleeping, when you're not stimulating your muscle to contract, the charge on the inside of the neuron compared to the outside is -70. So let me show you how this happens. So let's basically put a bunch of sodium and potassium ions on the outside and a bunch of sodium and potassium ions on the inside. So right now, it should be relatively neutral, okay? It's sort of equal on the inside compared to the outside. Sort of, okay? Don't count them now, but just assume that they're equal now on the inside and the outside. So how does it become -70? So what happens is this pump. This pump is called a sodium-potassium pump. You can see I mix the colors, green and yellow, or green and orangey, okay? Because this one can transfer both ions. Remember, these could only transfer their specific ion, but this one can transfer both, okay? So this is called a sodium-potassium pump, okay? Because it can pump both sodium and potassium. Now, what it does is, it's special. It takes 3 sodiums, you see, 3 sodiums, 2 potassium, and then it switches them around. So it's going to turn around. So now the potassiums will move in and the sodiums will be sent out. So this pump, this sodium-potassium pump, moves 3 sodiums out, 2 potassiums in. Okay? How can we remember that? This is my beautiful tip. Sodium is Na in chemistry, Na+. So, Na. It doesn't want sodium inside the axon, so it's going to move it out. Na. It doesn't want it. Na. Okay, so it moves it out. It wants potassium, so it's like, okay, I'll take potassium. So this is a good way of remembering that sodium, the axon, the neuron, does not want sodium, so it sends it out, Na, and it wants potassium, so it accepts it. Now, how can we remember that this pump moves 3 sodiums out and 2 potassiums in instead of 3 potassiums out and 2 sodiums in? How are we going to remember that? So I have a good way of remembering that. So, my second beautiful tip. So sodium, you can see, has 3 things making up. N, that's 1. A, that's 2. Plus, that's 3. So you move 3 sodiums out, whereas guess what? Potassium is made up of, ions are made up of 2 things, K and plus. So 2 things. So 2 are moved in. So these are 2 good ways to remember what's going on here. So now let's continue doing it. So it's going to take the next 3 sodium charge and the next 2 potassium, and it's going to do its magic. Whoop. And now 3 sodiums are moved out, 2 potassiums are moved in. Okay, so do you see what we're doing? We're moving 3 positive charges out and only 2 in. So overall, we're moving more positive things outwards than inwards. So after time, the inside will be less positive than the outside. The outside will be positive with respect to the inside, because we're only gaining 2 but losing 3 positive charges. So after a while, the inside will become negative with respect to the outside. So let's say right now it's -30. But now if we continue on doing it, so we take another 3, and then 2 potassiums, and it does its magic. Now guess what? Now it's even more negative. So eventually, if it keeps doing that, it's eventually going to reach -70. And once it gets there, it will keep it there. Okay, it will keep it at -70. It won't get less and less negative. It will make sure it stays at that level. So this is how naturally our neurons are negative when we don't stimulate them. Okay? So if you understand this concept of how it's naturally negative, now we can move on to understanding how this positive charge is formed and how it spreads. Okay? So here we go. This part should be nice if you understood the previous part. So I basically put now a bunch of, repeated this situation here. This is the normal scenario. So right now it's what? negative 70. We've got a lot of sodium that's outside because, the cell doesn't want it. It wants to keep it outside, and potassium a lot on the inside because the cell wants the potassium on the inside of the neuron, okay? Now what happens? So basically what happens now, wait a second, I need my positive charge. So what now happens is your brain will now send a positive signal. So pretend now the positive signal was sent to this neuron. Okay, so we look at this. So his brain now made a positive signal and put it into this neuron. Okay, so here we look at this neuron. It put it into this neuron. So how does this neuron now move this charge all along? So let's say here, the positive charge arrived now in this neuron. How is this positive charge going to move through like this? How is it going to move all along till the end of the neuron? How does that happen? Because right now it's negative 70. So I'm going to explain this using also a little diagram, okay? So right now we know when there's no positive charge yet, it's negative 70, the inside compared to the outside. So let's show that. By the way, here's the little table of what everything means. So here we have a little graph of time and membrane potential. Membrane potential is just this value I'm talking about, the charge on the inside compared to the outside. That's all that membrane potential means, okay? So we know that it's going to be negative 70 when there's no stimulation, when nothing is happening, when your brain sent no signal, right? So it's going to be like this. So it's going to be initially negative 70. Then what happens is your brain sends the signal being like, I got to whoop this guy's ass, right? I got to send the signal to this muscle. So here comes the positive signal, okay? This positive signal is very important because it makes this little bit right here, this part of the neuron, slightly less negative. So it makes it like negative 55, okay? It makes it a little bit less negative because this is a positive signal. Now, so what happens is this. So now the membrane, instead of being negative 70 in this specific area, it will be negative 55. So how does this look like? So see, there comes the signal. It moves slightly up to negative 55, okay? By the way, I'll just put this here as well. This is the definition of the resting potential. Okay, I just mentioned this already. Now, this positive signal arrived and we moved to negative 55. This negative 55 is called the threshold potential. Threshold potential. I'll define it just now because it's right here. I'm going to reveal it just now. The threshold potential is a charge at which these sodium channels open. Okay, normally they're closed. Okay, it's like a gate. Only when it's negative 55 charge can this gate open. Okay, so now that we've reached this threshold potential of negative 55, the sodium channel gate can open. Okay, when the sodium channel gate opens, we know that these sodiums can come into the neuron. When they come in, now since they're positively charged, they will make this area positive. Okay, because before they came in, this area was still negative compared to the outside. So now as they come in, they make this side even more positive. Okay, they make it much more positive. And so as they come in, now this positive charge, instead of being only here, it moves. Because now this area is more positive. And now since this area is more positive, the charge of negative 55 is not only here anymore, now it's been moving. Now it's also negative 55 here. So now that it's also negative 55 here because of these sodium ions that came in, now this gate will also open. So when this gate opens, guess what? Sodium comes in. And now guess what? The sodium now is making this area also positive. So this positive charge is moving along. And now, since this area is now also positive, or this area also reached the threshold potential of negative 55, this channel will also open because now this area is negative 55. It's reached the threshold potential. So now sodium comes in. Okay? And now again, now this area is positive and now this area is activated. So now even this gate will open and even more sodium will come in. So this is how this positive charge spread all the way from here through the axon till the end. Okay, So this is called when sodium comes in. So at first, remember, this positive signal had to be negative 55, okay, so that this channel can open. And then when sodium comes in, it goes all the way up till plus 30, okay? Okay, so bear that in mind. So initially, when there's no sodium on the inside, and we get a signal from our brain, the positive charge moves from negative 70 to negative 55. But when it reaches negative 55, these channels open, allowing sodium to come in, okay? And when sodium comes in, now it goes up all the way to plus 30, because now all these positive charges are coming in, making the inside much more positive compared to the outside. Okay, so let's look at this on the diagram. So we had this signal sent, reaching the threshold potential. The threshold potential now allows the sodium channels to open. Okay, if the sodium channels open, a crap load of sodium will come in. Okay, a crap load of sodium comes in. Okay, and this makes the impulse spread all along the neuron. Okay, so this impulse, the meaning of impulse is just the spread of this charge through the neuron. Okay, so now what happens is these potassium ions have not opened yet, right? Because they only open, guess what? When it's plus 30. So now that all the sodium channel ions came in, now the charge on the inside is plus 30. Plus 30 stimulates these sodium channels to close, okay? So they don't work when the charge is too high. They only work when it's a bit lower than that. But the potassium ions opens when it's plus 30. So now that it's plus 30, the inside is so positive compared to the outside, now they open. And guess what? Potassium will now leave. And what causes them to leave? So what causes them to leave is concentration gradient, right? The inside is there's so many more potassiums on the inside compared to the outside, so it wants to leave. But also, another thing causes them to leave. It's so positive on the inside that it's like repelling each other. So they also leave due to the charge. So they leave to both the electrical charge and the concentration gradient. That was the same reason that sodium came in, remember? Sodium was on the outside initially, and there was no sodium on the inside. So both the concentration gradient caused sodium to come in through this channel and the charge, because the inside was very negative, very negative. So this positive charge was kind of attracted to it, okay? So we call this the electrochemical gradient, okay? When there's both an electricity gradient and a chemical gradient that causes the ions to move, right? So both the concentration gradient cause potassium to move out and the electrical gradient. It's too positive on the inside, it's repelling it to go out, okay? To this negative outside. So again, they all open, potassium rushes out, and what happens when potassium goes out? That means positive charges are leaving, meaning the inside now becomes more negative, okay? So all these positive charges are leaving, they're all sent out, okay? So now the inside is extremely negative again, but it's so negative that it's negative 90, okay? So it moves. Remember before when you're at your resting, when your muscle is doing, when your neurons are doing nothing, it's negative 70. But when all the potassium leaves, it goes down all the way to negative 90. Okay, so let me show you here. By the way, here's depolarization. So when sodium comes into the neuron, as I mentioned before, that action of coming in is called depolarization, okay? That's this dark blue line, depolarization. Now when potassium leaves, it's called repolarization. So I just said, right, all the potassium rushes out and goes down to below negative 70, to like negative 90, okay? So that's where we're at now. Now what happens is, the whole purpose was done. We managed to move this positive charge all the way through, right? So now this neuron, now this positive charge is like over here, okay? It moved all the way through the neuron, okay? But now this neuron needs to reset itself so that it can receive another impulse if it wants to contract again, okay? Because right now it can't receive another impulse, okay? It can't. It needs to reset itself. So to reset itself, it uses these sodium potassium pumps, okay? So first, all the potassium channels will close, okay, to prevent more potassium from leaving. So now we're at negative 90, and now these pumps will take 3 sodiums, remember 3 sodiums, 2 potassiums, and switch them around. Okay, so eventually, of continuously moving 2 potassiums in and 3 sodiums out, we will just reset the whole thing. So all the potassiums will end up being inside, and all the sodiums will end up being outside. Okay, so it's basically reset to how it was before. So now it can basically receive the next signal from your brain. So that's the last bit here. So we just did a repolarization. Repolarization was when the potassium ions all went out, causing the inside to become more negative, until it went so low to this point. Now at this point, this is called the refractory period. Okay, the refractory period is when it's at like negative 90. Okay, and you can see now the refractory period goes up to negative 70 again. Why? Because this pump returned everything back to normal. It pumped all the sodiums out and all the potassiums back in, returning it to negative 70. Okay, that's it. Now we're back again at the resting potential, waiting for the next signal to arrive. So that's all we need to know. Like I'm going to show you some definitions you're missing, but this is the whole process. A good way, if you can't remember this, is this. Pretend like the sodiums is a criminal, okay? They're on the outside of your house, okay? This is your house. The inside of the neuron is your house. This is where you live, okay? And basically, the criminals, they enter through a specific weird location, like a window or a chimney or something, and they come in. And when all the criminals come in, you see them, you're scared for your life, so you exit through the door, you run out, okay? So you're basically the potassium, and the criminal is the sodium. So the sodiums, the criminal comes in, as soon as you see them, you peace out. You go out of the house. So now the sodiums are on the inside, and the potassium is on the outside. And now we have the police come. You call the police, they come. They're basically this thing. And they're gonna make sure that this criminal gets out of your house and you get back into your house, okay? So you can remember this little analogy if you really have trouble remembering this. Okay, definitions. Impulses, I mentioned this before. Impulse is basically the process of sending this little positive charge throughout the neuron, okay? So I'll just spread them out here for you to see. I mentioned already the electrochemical gradient. It's the combination of the concentration and the charge difference, remember? And last one you need to know here is saltatory conduction. So basically, this signal is sent throughout the neuron, right? Now, saltatory conduction is the job that these little myelin sheaths do. They speed up this conduction. So that's all that saltatory conduction is. They speed up this process. Okay, so I think that's it. I'm just double checking. So basically, now we're at this point, and in the next video, I'll show you how this positive charge is transferred from this neuron to the next one, okay? Because then if we know how this happens, we know how it transfers inside the neuron, and then we get to this spot where it just contracts the muscle. So then we'll be able to solve how Stipe Miocic managed to punch this guy back, okay?